Hello everyone, I hope you guys are doing good and studying well. Well, in the last video I have discussed about the potential energy, and in the continuation of that, today we'll be talking about the potential. So what we have done in the last class was only to make sure that we get less difficulties in solving numericals. When we start solving with all the forces inclusive, it becomes difficult. But with the concept of potential energy, a lot of questions could be done quite easily. Now, so potential energy was the characteristic of the field and a charge placed in that particular field. Whereas today we're going to try and focus only on the characteristics of the electric field. Let's say, for example, if I try to relate this with the gravity, if I move object, let's suppose from point A, which is at 5 meter above the ground level, to to a 10 meter height. Well, to move a block, let's suppose mass is 10 kg. From here to here, I need to do some amount of work, right? And that is stored in this mass as a potential energy, gravitational potential energy, because I'm doing work against the gravity. So this height, this particular point is defined to be at a height of 5 meter, right? And this particular point is defined to be at a height of 10 meter. So there's a difference in the height. We have delta H. In terms of electric field, I should be having some values, some sort of tools to define the potential of one particular point, right? In an electric field, I should know what is the value, how much work do we need to do. Let's suppose if I have a point A over here, I want to move a charge to point B. Okay, I have, let's suppose, some electric field existing in this region. Then I should be knowing how much work I need to do in moving the charge from this point to this point. Of course, because I'm moving a charge, there should be some amount of change in the potential energy. So what's happening over here, I'm trying to move the charge from one particular point which is having a different characteristic, which means impact of electric field, to another point which have different sort of impact of the electric field, maybe in the terms of distance, and that is called potential. So basically, when we talk about the potential, we deal with the characteristic or the influence or the impact of the electric field at that particular point, irrespective of the charge present at this point, or whatever point, irrespective of what is the value of the charge present. When we were dealing with electrostatic potential energy, the charge was into the picture, right? If you remember, U is equals to K Q Q2 by R. Right? In this we had this charge used or emphasized over there. But if I want to know only this particular point, as in only height I want to discuss, I don't want to discuss about the potential energy. Over here it's going to be how much? 5G. Over here it's going to be how much? Your 15G, right? mgh. So of course you can just put a m over there, which is 10. So we have a difference in the potential energy. But these two things gives you about the position of these 2 points with respect to earth. Likewise, the potential going to deal about the electric field influence over there irrespective of the charges. Let's say for example, if I have a positive charge of, let's say, 1.6 electron charge, let's say a positive electron charge, that is 1.6 times 10 to the power of minus 19 coulomb in certain electric field, such that the potential energy at that particular point is, let's say, 4.8 times 10 to the power of minus 17 joule. Let's assume that. Now, what is going to be the charge energy per unit charge? So energy per unit charge should going to be how much? 4.8 times 10 to the power of minus 17 over 1.6 times 10 to the power of minus 19. Well, that's going to be 300 joule per coulomb. Now let us increase the value of charge at that particular point. Let us increase the value of charge. Now let's say the charge over there is 2 times of E. Well, that's going to be positive. I'm taking the positive in magnitude just to avoid any sort of. So 2 times of that coulomb. Now the energy will increase, of course, because the energy is Q12 K Q1 Q2 by R. So the energy will be how much? 2 times of that. That's going to be 9.6 times 10 to the power of minus 17 joule. Let us find the energy per unit charge. Energy per unit charge. Well, that's going to be 9.6 times 10 to the power of negative 17 over 2 times of 1.6 times 10 to the power of negative 19. Well, it's going to be how much? Again, it's going to be 300 joule per coulomb itself. So you can say that per unit energy, the charge energy per unit charge remains same, and this is called your potential. So the potential is defined as energy per unit charge. Fair enough? And this is going to be constant for a particular point, a particular position in the electric field. So I can say that electrostatic potential is a characteristic of electric field, not of the charge present in that. Fair enough? Now, having said that, let us try and find the, how to formula for this potential. So I know that we represent this with V is equals to U by Q. Okay, now let me use the black one. Okay, so let's suppose this is charge Q naught. So as we know, U is nothing but K Q naught by R, and this Q naught 1 by Q naught will be nullified. So I can right away say V is going to be KQ over R. This Q is the source charge due to which the electric field is produced. Well, so V depends on the position R. It does not depend on the test charge being present. It's purely a characteristic of this charge, right? So this Q is source of electric field. So I can quickly say that electrostatic potential is the characteristic of the electric field. So it must follow the rules of superimposition. Electrostatic potential is a scalar quantity. Okay. Now they're going to be, if I have multiple charges being present, then that will influence the electrostatic potential at one particular point. So if I want to find the net potential, I'm going to add them up with the scalar rules and all. Simple as that. Alright then, now let's talk about the potential difference. For example, potential difference. The next is potential difference. So I have discussed about the potential of one particular point. If I want to know the potential difference, I must be knowing how much work is done or required to move the charge, how much change of energy taking place if the charge is displaced from one point to another point. Let's say from this point A, a charge is moved to, let's say, a point B. Okay, I'm using that Q naught is moved in this under the some electric field. Now there should be some change in the potential energy. So potential of a point is a potential difference could be defined as change in potential energy per unit charge. So by saying that, I can write potential difference, let's say potential difference of A and B could be written as change in potential energy per unit charge. Understand these things properly, okay? I'm sure a lot of people get confused with the signs and all. So this is the potential difference of point A with respect to point B. You can write down this is potential difference of point A with respect to point B, VAB. Now this could be written as U final, that is U at B, minus U initial, that is at A, over Q naught. Fair enough? Now we actually know that delta U is nothing but, if you remember the previous class, delta U is negative work done by the conservative force, right? If you have not seen my previous video, go and watch that. I have explained the potential energy quite nicely over there. I'm going to put the description, link in the description as well as in the I button over here. Okay, now delta U is known as minus of WC. Can I just write this as, okay, let me use it here. Let me put it up here. So VAB could be seen as negative of work done by conservative force. Okay, so with this I can actually define the potential in one more term, that the potential difference of points is defined as negative of the work done by the conservative force in moving the charge from one point to another point. I'm writing it here, negative of work done by conservative force, work done by conservative force. Over here the conservative force is your electrostatic force in moving the charge, You can define it this way also, right? So potential change per unit charge from A to B, or the negative of the work done by the conservative force. Okay guys, using these two things, let me just continue from here. Can I just write VAB is nothing but if I look at this part and this part over here, minus of WC, can I just write minus of delta U by Q naught? Okay, so that's gonna be U minus of UB, I'm writing in this reference, UA over Q. So that could be seen as minus of VB minus of VA, because UB by Q is going to be the potential of point B. So ultimately I can say VAB is equals to VA minus VB. Just remember this, that's all. Fair enough? I'm sure you guys have understood the meaning of potential difference and the potential. Now what next? Now we're going to be talking about the different figures, different bodies in which we have to find the potential. We're going to see some numericals based on the potential, and we're going to see how the potential and the electric fields are related. The majority of the questions will be coming up over there. Okay, so you'll be coming across this word quite some time. So this is the energy acquired by electron charge when it is accelerated by a potential of 1 volt. So this is nothing but 1.6 times 10 to the power of minus 19 coulomb times 1 volt. So this is going to be 1.6 into 10 to the power of minus 19 joule. So when an electron charge is accelerated by 1 volt, it actually acquires some energy, and that energy is given as 1 electron volt. Now electrostatic field, electrostatic potential is a characteristic of the field, so it should follow the law of superposition. So let's suppose if I have if I want to find the net potential, this is going to be V1 plus V2 plus Vn. Now V1 could be given as K Q1 over R1 plus K Q2 over R2, so on, plus K Qn over Rn. I'm going to take out K common, so I can write sigma of Qi over Ri, where I stands from 1 to n. So this follows scalar addition. All right. Now if we have continuous charge body, then I'm going to put it here only for continuous charge body, V is going to be nothing but integration of dV. dV is nothing but K dQ, right, over R. So I can actually figure out these things. I can do integration of this. So that's going to be for the continuous charge body. Simple as that. Okay. Now if I move, what happens if I move a positive charge from lower potential to higher potential? Will the energy increase or decrease? Let us quickly see that. Let's suppose if a positive charge is moved, let's say Q is a positive charge, it is moved from A to B. Assuming that VB is more than VA. Okay, VB is more than VA, it clearly means that B is closer to the electric field, right? So what I'm doing over here, we know that potential is nothing but negative of the work done by the conservative force over a charge in moving from one point to another point. Now let's say if it is moving from a lower potential to higher potential, let's say that's going to be delta U by Q, that is U final minus U initial over Q. U final is going to be more than U initial, lower potential to higher potential. It means if I look at the magnitude, guys, the work done going to be higher in negative, it means decreased, negative work is done. Agree or not? If suppose at this particular point, if the potential is 10 volt and it is 20 volt over here, so what is the potential difference? Potential difference is nothing but 20 volt minus 10 volt. Okay, so I'm going to have 10 volt of potential. Well, if I look at this, magnitude is how much? 10, and this is positive. It means work done will be how much? Negative, right? So I can say that work done by the conservative force will be negative 10 Q, right? Okay, let's say joule. If the work done is negative by the conservative force, what happens? We have done in the electrostatic chapter, electrostatic potential energy. If the work done by the conservative force is negative in moving the positive charge, it means the energy of the system will increase. If you, again I'm telling you, if you have not seen that video, please watch the previous video of electrostatic potential energy. I'm gonna give the link in the description as well as in the I button over there. Okay, you can check it out. So when the work done is negative, the potential energy increases. Likewise, if I move a negative charge, from lower potential to higher potential, potential energy will decrease. energy will decrease. Very simple. Because what happens over here, the negative charge, this becomes positive. If it becomes positive, means work done is positive, means the work is done by the system, by the conservative force, so the energy of the system will decrease, isn't it? Yep. Now let us see some questions based on this stuff. Now later on we'll be talking about relation of potential in the electric field. Of course we need to relate them, because potential is a characteristic of the electric field, so we must be having some mathematical tools to relate them as well. Now there are going to be some point in a field, in a region, at which if you have multiple charges, there could be potential could be zero, right? Now let's say I have an arrangement over here. Let's say I have an arrangement such that I have a charge Q placed over here at the origin, and I have, let's say, minus 2Q being placed over here at a distance of, let's say, 6. So these numbers is chosen for actually coming, getting a good answer. That's it. I can actually get do it with the 2A in general. I'm just choosing a number for your better understanding. Now electrostatic potential, as we know, is a scalar quantity. It means at this particular point, let's say, because of this I'll be having a positive potential, and because of this I'll be having a negative potential, right? But this magnitude is more compared to this. It means the field, the point should be kind of away from here in order to have zero potential. So let's say this one is here and this one is here at a distance of r1, at a distance of r2. Let's say this point is P at V is equals to 0. At this point V is equals to 0 at point P. Now my question to you, find the locus of point, find locus of points having V is equals to 0. Simple as that. Well, it's not like only one point could be there, could be multiple points at which the potential could be 0. So that's what we have to work out. Okay, let's say this point is at a height of y from here and x from here. The distance be x from here. Alright, now let me come to this side. If this distance is x, I'm sure you guys agree that, okay, this distance is going to be how much? 6 minus x. Simple as that. So the net potential at this particular point P, V should be V1 plus V2. Let us assume that potential V1 is because of this charge Q and V2 is because of this charge minus 2Q. So this is going to be K Q over R1 plus V2 K minus 2Q over R2. Well, R1 could be equals to how much? X square plus y square under root, isn't it? Whereas R2 should be how much? Y square plus 6 minus x whole square under root. I can write it in the terms of power also. I'm going to substitute it over here and then I'm going to work on this. Simple as that. Okay, let's get one part of this. We know that V should be 0. It means K could be taken out common. I'll be having KQ common. I'll be having 1 over this R1. That is going to be x square plus y square under root plus KQ is taken out common, so I'll be having minus 2. Let me put it minus 2 over 6 minus x whole square plus y square under root, and this should be how much? 0. As per the given condition that potential should be 0. Alright then. Now let me take that side. I'll be having how much? I'll be having 6 minus x whole square plus y square under the square root minus 2 times of x square plus y square equals to 0. Fair enough. Let me take it that side. So what I can do, I can quickly say this is this. Squaring both the side. Squaring both sides. I'm going to be having 6 minus x whole square plus y square equals 4x square plus 4y square. Easy. Simple as that. Let us open this sign. This is going to be how much? Well, I'll be having 36x square minus 12x plus 36 plus y square equals 4x square plus 4y square. Okay, let us put them in one side. I'll be having 3x square taken that side. I'll be having 3y square plus 12x, okay, minus 36 should be 0. Let us try and take 3 common out. I'll be having how much? I'll be having x square plus y square. Fair enough. I'll be having plus 4x minus 12 equals to 0. Alright guys, let me just clean a bit of this part. So by doing that, I can actually have a little bit of place for me. Now over here, I can actually make a perfect square from these two things, right? That's going to be nothing but x plus 2 whole square minus 4 minus 12 plus y square is 0. You can see how to do the perfect square. So it's going to be x plus 2 whole square plus y square is equals to 4 square, 16. Well guys, this is nothing but equation of a circle, isn't it? So the locus of the point will be a circle with the center minus 2 comma 0 and the radius equals to 4. It means I'll be having a circular track, circular path in which the potential is going to be 0 because of this charge arrangement. Simple as that. Now we know that electrostatic potential or electrostatic force is a conservative force, so work done will be conserved, right? Momentum will be conserved, for the energy will be conserved. Now let's say I have done some questions in the previous videos that to find the minimum distance of approaching charge. Okay, let's say on that, in the continuation of that, for example, if I have, let's say, example 2. Alright, then let's say if I have probably a charge of 2 coulomb over here, or 2 electron, I can just choose to have 2 electrostatic, 2 electron positive charge over here, or maybe let's keep it 2 coulomb, simple as that. If a charge of, let's say, 50 coulomb is here and it has it's approaching it with a certain velocity v, having kinetic energy, let's suppose 10 megavolt. Now what is going to be the closest, the shortest distance between them? Let's suppose this charge is here, this charge is here. Once it approaches it at certain distance, it will stop. So let's say this is q1, this is q2 of these values, and the distance between them is r. If it is approaching it with certain kinetic energy, with velocity, it will come over here and it will stop. After that, it won't be going further closer because of the repulsive force. So what happened over here? Electrostatic force is conservative force, so the energy will be conserved. Energy is conserved, isn't it? So initial energy is equals to final energy. Initially what we have, if I assume this is at rest, initially how much energy it has? Only kinetic energy, right? And finally we'll be having some potential energy. So can I say, guys, kinetic energy, which is initial energy, should be equals to the potential energy. Let's suppose k q1 q2 by r. Well, that's going to be how much? So I need to find this r, simple as that. So that's going to give me r should be equals to how much? K q1 q2 by this kinetic energy, which is 10 to the power of 6 electron volt. Fair enough. Electron volt could be given as nothing but 1.6 10 to the power of minus 19. Fair enough. Now here put the values of these charges and all, and again solve it. That's going to be the minimum approach, minimum distance of these two charges and all. Okay. Now let us try and quickly define the relation between V and E, which that's really important to understand because we'll be having a lot of questions based on that concept. Okay, guys, we know that. Now next heading, relation between V and E. Right? Okay. Now we know that change in potential energy delta U is nothing but negative of the work done by the conservative force, and this is going to be how much? Let's say U final minus U initial could be given as, okay, or let's say if I try and do this way, for small du should be how much? Negative of small work done by conservative force. Now to get the total energy, I'm going to integrate both the side. Okay, let's say this is U initial to U final, this is U, okay, don't be mistaken, that's U final. So I'm going to have U final minus U initial should be negative of the work done by the conservative force. What is conservative force over here? Electrostatic force. Well, that's going to be nothing but Q times E. Let's say it is displaced by small distance dr. So that's how it's going to be. Let's suppose from R initial to R final position. Initial could be infinity, could be any particular point. I can choose any point, Let us take this Q out. I'll be having how much? UF minus UI by Q. That's going to be E dot dr, guys. U minus of R initial to R final. Now, having said that, that's going to be how much? UF by Q is nothing but final potential energy minus initial potential energy, that's nothing but minus of E dot dr, Ri to R final, right? Now let's say, now if I do this way, Vi minus V final, that's going to be E dot dr. R initial to R final. Just remember this, things will be taken care of. Let's suppose R initial is infinity. If I'm starting it from infinity and bringing this charge to a certain point, I can right away say that V is equals to minus of E dot dr, because Ri should be infinity and that's going to be Vi should be 0, so minus of Vf should be this, so V should be minus of E dot dr. You remember this and do not forget this negative sign. We'll be doing some questions on this, right? Now one more thing I can tell you, I want to tell you over here, that this could be seen as V equals E dot dr. If I look at this thing, it means E dr cos theta, right? Now what if the direction of electric field and the displacement is not in same direction? They could be in different direction also, right? So that is going to be the case when we have the electric field in different direction, not in the same direction, making some angle. So in those cases, what we do, we take the component of the electric field and the dr displacement over there, and then we work on that. Okay, so let's quickly see some concept on that and some question on this. Alright then, now let's see what happens if the electric field is along this direction, let's suppose, and the displacement of the charged particle is, let's suppose, in this direction, making some angle theta over here. Now I should know this angle, of course, so what we do, we just try and find the value of E along this, or maybe along this, simple as that. Now let's suppose if you have a point charge over here, it will be actually having the electric field outward in all the direction. If suppose a point charge move from one point to another point in, let's suppose xy coordinate, the dr and E will not be in the same direction, right? So what we need to know, we in this case is what we do, we find the component of the field along the displacement direction and of course the displacement direction component, and then we get the dot product of that. Quite easy. Okay, so what exactly we have when the charge is moving, then your E will be taken as, you will be having Ex I cap plus Ey j cap plus Ez k cap. All okay. Now we know that, and of course dx should be, your dr should be along dx I cap plus dy j cap plus dz k cap, will be dividing it over there. We know that V is equals to negative of E dot dr. It means E could be given as negative of, I can say dv by dr, right, over here, change in, so dv, small dv is equals to minus of dr. Okay, if I want to find Ex, if the charge is moving along the x direction, then from here I can say that Ex should be nothing but minus of dv over dx. Fair enough. Likewise, Ey should be negative of dv over dy, and Ez should be changing the potential along z direction. Simple as that. Fair enough, guys. Now, so this is Ex, Ey. So this is used when the charge is moving along the x direction. Okay, when the charge is moving along the y direction, when the charge is moving along the z direction. So if I have any electric field which is variable, I can actually get the electric field. I can probably use this thing and I can solve it. Simple. It's not a big deal. Likewise, dv should be. So over here, what happens in this case? What we do, we use a partial differentiation. All right. If the particle is moving only along the x direction, I should be only considering the electric field along the x direction. So here comes the concept of that's partial differentiation. So basically what we do over here, when the particle is moving along only the x direction, then in that case Ax should be minus of dou v over dou x. Fair enough. So when we're talking about the x and y and z individually, I'll be using the concept of partial differentiation, dou v over dou y and all. Okay. So let us understand this concept quite in detail with one problem. Okay. Now let's see that. Let's have an electric field in such a way that it is given as probably let's suppose probably we'll have a potential or maybe electric field, or maybe let's have a question. V is given, or the potential, it's a scalar quantity basically, so let's V is given, it's a variable, electric potential is given as probably, let's say we have xy square plus, let's say x square z or something. Okay, so you can see that this is along the three variables, both xy and z, right? Now they ask you to find the, let's suppose, electric field at any point. Probably they can use the point, let's suppose 2 comma 2 comma 1. I want to find electric field, find E at 2 comma 2 comma 1. What do we know? Since the field is based on both x, y and z, I have to find at these particular point. So I'm going to find Ex. Ex should be how much? Minus of dou v over dou x. This is a partial differentiation. When I differentiate this with respect to x, it means y and z should be taken as a constant. That's the meaning of partial differentiation. Well, that should be how much? In this case, keeping x as y as constant, only x is a variable, I'll be having how much? Negative y square. This part is going to be 0 because they are constant with respect to x. Likewise, Ey should be a negative of dou v over dou y. Now I'm going to put y as variable and the remaining everything else other than y should be constant. Now in this case, I'm going to have 2xy and this part is going to be 0. Likewise, we'll be having Ez, that's going to be dou v over dou z, and that's going to be how much? X square minus x square. Right, now we get to find the electric field at this particular point 2, 2, 1. So this electric field will be how much? Ex, okay, let's put the values. Ex should be how much? Y is 2 minus 4. This is going to be 2 times 2, 4 times 2, 8. Okay, negative sign, negative sign. This is going to be how much? Minus x square, so minus 4. Okay, now so Ex, I'm going to represent that with the I, J and K, unit vectors, right? So the net electric field E net should be minus 4 I cap minus 8 J cap minus 4 K cap. And if I want to find the magnitude of this electric field, simple, I'm going to take 4 square 16 plus 64 plus 16, and whatever comes will be your answer. I'm sure you guys have understood this. Okay, let us see more questions based on this. Now in this question I have taken the V. Now I can actually go ahead and check. I can choose E, and then probably I can ask you to find the value of V. Okay, let's do one. Let's see example 1. If let's suppose E is given as 2xy I cap plus x square j cap. The electric field is variable over here. Now I might ask you to find potential at let's say point B. Maybe I can put 2 comma 3. Let's say 2 comma 3 if potential at A with a coordinate, I can choose to have 2 comma 1. Anything you can choose. Let's say 2 comma 1 is, let's say, 15 volt. Okay, now in this case you can see that the electric field is variable, right? So what I'm going to do, I'm going to find the voltage. You know that V initial minus V final is equal to integration of E dot dRe. Normally we have V final minus A initial is minus. I'm going to choose, right? This is the best used formula. Vi minus Vf is going to be equals to E dot dr. Okay, that's okay. Vi, that is going to be Va minus Vb. Initial at A minus Vb. That should be how much? E dot dr. What is E? 2xy I cap plus x square j cap. Now as I've told you, I'm going to take this dr in terms of dx I cap plus dy j cap. Okay, now V is how much? 15 volt minus Vb, that should be integration of 2xy dx plus x square dy. Now this is a very typical integration. You guys might have done it. When we have this kind of cases, what do we do? Let's k equals to, in this case what exactly we do? We have to choose a value for k, such the derivative comes equals to this, right? If I choose x square y, if k is equals to x square y, let's see what happens. In this case dk by dx should be how much? 2xy plus x square dy by dx, isn't it? So here I'm going to have dk equals to 2xy dx plus x square dy, right? Fair enough. So I can actually say that this entire thing will be nothing but 15 minus Vb should be equals to this entire thing. You can see that 2xy dx plus x square dy will be nothing but dk, isn't it? Now let us put the limit for k. k is equals to x square y. Now initially a is 2 comma 1, x is 2, 4 into 1, this is going to be 4. Final b, x is 2 square, 4 times 3, how much? 4 times 3, 12. Right? Now if you have this case, I'm going to have how much? Sorry, 2 comma 3, yeah. So this is going to be k, 4 and 12. I'm going to have 12 minus 4, which is 8. So VB should be 15 minus 8, which is how much? 7 volt. Right? So the value of potential at VB should be how much? 7 volt. Agree or not? Likewise, we can have questions on this. Now they might come up with the graphs also. They might come up with the graphs in this case, graph of E and X, So in the graph what we have, area we take. Area is the E dot X will be how much? Area, and E dot X is nothing but your potential. So what I mean to say is, let's have a quick understanding of that. If they give you questions in the graphical form, you don't have to worry about that. You can do it quite easily. Let's say if I have a graph like this, E versus X graph, E versus let's say R. The graph is something like this. Let's suppose here we have, okay, let me just make it like this, okay, and this, something like this. Now they ask you to find the potential of this. Simple, take the area of this part, take the area of this part, area of this and this, we'll add it up, we'll be getting, because this is going to be area under this curve is how much? E into dr, right? Well, that's nothing but your potential with minus sign. Simple as that. Sorry. They might give up the value. Let's suppose this is probably 2 comma 0, let's say 4 comma 0. You can get the area. Let's say this height is 10 or something, So area of this triangle is going to be half 2 into 10 by, that's going to be how much? 10. I'm going to have 10 volt over here, and this will be how much? This is going to be how much? Oh, solve kar lete hain isko. Let's solve it. Area of this part will be how much? Half into base into height, plus area of this part is going to be, this is 2 times 10. I'll be having 10 plus 20, 30. So V is equals to how much? Minus of 30 volt. Fair enough, guys? So they can give you questions with the variables, electric field, or maybe the graph. Don't worry, just follow these basic steps, you'll be done. Okay, let's quickly go ahead and check if they give you the figure, the electric field in terms of making some angles and all. Let's see what we do in those cases. And I'm sure you guys know that if field is 0, it does not mean the potential is 0, right? And if potential is 0, does not mean also the field is 0, isn't it? So if I say electric field is 0, potential is 0, it is true or false? It's going to be false. It's not necessary. At electric field at certain point, probably over here, in certain cases electric field could be 0, but the potential might not be 0. For example, inside a disk, inside a circle, inside a ring, the potential is maximum at the center, though the electric field is 0 over there, right? Electric field is 0 at the center of the ring. If I have a, let's suppose, positive charge being over here, E over here is 0, but V not equals to 0. I'm going to teach that in the today's lecture only, that the potential is maximum at the center of the ring. Okay, now they might give you that, okay, potential is 0. Does it mean that E is 0? Again, no, it's false. It's again not true. Let's say, for example, guys, if you have, I have a square, let's suppose if I have a plus q over here, let's say minus q over here, let's say minus q over here and plus q over here, at this particular point, the net field will not be 0, but the potential will be 0, isn't it? The field will be, because of this and this, in this direction, because of this will be in this direction, will have the net field over here in this direction, right? But the potential going to be 0, because they are equidistant from the center and we have two equal and opposite charges, so net sum of the potential will be 0 in this case, but the field will not be 0. Okay, I'm sure you guys have a hang of it. But yeah, that's great. Let's quickly move on. Let's say they give you some example like this. Let's say have example. Let's say in xy coordinate, we have the field lines in this direction. Okay, let's say we have E0 field line in this direction, making some angle of 53 degree with x-axis. All right. Okay. Now let's say I'm moving from one point to another point. Let's suppose from this is my point A, this is my point B. Let's say this is A. Probably I can choose x as, let's say, 2, 1, and let's say B as probably 4, 3. I want to know what is the potential difference of VA and point B. Okay, no problem. Again, I'm going to do the same thing. I'm going to follow the basic rules. VA minus VB. Initial minus final should be how much? E dot dr. Now we're going to find the component of E along this. I'm going to find the component of E along this also. Right? And that's how we're going to work out. So the E should be given as how much? E naught cos 53 dx, right? So E naught cos 53 is how much? 3 by 5 dx, isn't it? Fair enough? Or maybe you can choose I cap, no problem. Let's I cap over here. Plus E naught sine 53 4 by 5 j cap. Okay, let me write it here. So this should be your E naught, if the field is E naught cos 53. If this angle is again gonna be 53 only, isn't it? Yeah, cos 53 is nothing but 3 by 5 I cap plus E naught sine 53 will be 4 by 5 j cap. Okay, integration dr is going to be from A to B. That should be how much? 4 minus 2 I cap, and this is going to be 3 minus 1, again 2 j cap. Simple as that. Now we can do it, isn't it? Yep. So that should be whatever it is, you can calculate it quite easily. So it's going to be 3 by 6 by 5 E naught, plus I'll be having how much? 8 by 5 E naught VA minus VB, and you can get it done. Isn't it? Easy one. So that's going to be the value for this case. When we have electric field coming up in this case, we'll add it up, we'll get the answer, we'll get the potential difference. So that's when we have the variable electric field coming up into the picture. What we do, we follow the basic rules. We get the components of electric field in x, y and z coordinates. Likewise, we get the components of dr in x, y and z coordinate. We go with the partial differentiation if the particle is moving in, probably if it is moving and making an angle of, as you can see in this way, it's moving along x and y direction both. If it is moving only in the x direction, I'll be taking partial differentiation of x with respect to x. In the y, I'm going to take the partial differentiation of y. Fair enough, guys. Now let's talk about electric field due to potential due to some known figures, right? I'm sure we have done electric field because of dipole, because of ring, because of disk. Now we can actually do some more sort of calculations with that. Okay, let's do it. Now let us talk about electric potential due to a conducting sphere. Okay, let's keep it hollow or solid, doesn't make any difference, because in hollow and solid both the charges will be appearing at the outer surface of the sphere. Okay guys, let's suppose if I have a sphere, okay, and the charge plus q is given over here, so charge will be distributed. I'll be making different separate videos on the cells. We get a lot of questions on the cells in the cavity. I'll be doing that after teaching you the Gauss law. Anyways, let's suppose we have this, let the radius of this sphere be r. Okay, now I can have three cases in this, not in this, in everything. The first case at finding potential at point inside the sphere, second could be finding potential at the surface of the sphere, and third could be anything outside the sphere, right? So the first case, r is less than capital R, this distance, let's say r. Second case, r is equals to r, and third case when r is more than r. So these are the only three cases when we have to find the potentials, right? Potential is how much? Kq by r. All right then guys. Okay, I know if it is a metallic conductor, it's a solid metallic conductor, then the field inside this will be how much? 0. Now since field is 0, so there won't be any work done required to move a charge from this point to this point or to any point inside the conductor. So whatever work, so all the points inside this will be at equal potential. I've discussed it in the beginning also. Now then I'm telling. So whatever potential we have at this point will be the same potential prevailing at any point inside the sphere. I'm repeating it one more time. So if I want to move a charge, let's say let me use a different color. If I want to move a charge from here to here, there won't be any work done, because the E is 0. When E is 0, force is 0. When the force is 0, no work is done. So the work done in moving this charge will be how much? 0. If the work is 0, the potential difference will be 0. It means every point inside the conductor will be at same potential. Agree or not? So the potential at point A should be equals to potential at point B, that is on the surface of the sphere. Well, that's going to be how much? Kq by capital R. isn't it? So the potential inside the sphere and on the surface of sphere is kq by r. But the moment I come out of it, let's suppose at this particular point at a distance of r from here, this sphere start behaving like a unit charge, as a point charge. Then the potential at this particular point C, Vc will be how much? Kq by r. Simple as that. So if I look at the graph of this sphere and the potential and the distance versus that, let's suppose this is the potential, this is my distance r, then from here till the surface, right, we'll be having same potential, isn't it? We'll be having same potential. That should be, let's suppose, constant. That's going to be how much? Kq by r. From the moment I reach, when r becomes equals to r, it will start decreasing inversely with r. So this is going to be something like this, isn't it? So let's say this is 0. So the potential from the center to the surface will remain same. After this, that's going to be decreasing. Now we can have a solid non-conducting metallic sphere, right? Like solid non-conducting sphere. It cannot be metallic, of course, In that case, we have to solve. In that case, the potential at every point will be different. Okay, so guys, you can try that as a homework. Because of time constraint, the video size will get increased. So in the next video, I'll be talking about the potential at these 3 points with respect to a non-conducting sphere, because of dipole, the work by dipole, because of line charges, because of ring, because of disk. I'll be discussing all these things, potential of all these things, in the next video, and I will relate that how to do things quite easily with the help of potential and electric field together. All right, guys. And yeah, if we have a good amount of knowledge about this potential electric field, I'm sure a lot of questions will be done. Okay, now after this we'll be getting into the Gauss law, and then I'll be getting into the conductors, phase conductors, and then the next topic is going to be the capacitor.